All right, we are going to start into momentum. And this unit or part of this unit is, well, it does build off of the things we've been through so far. So, forces, energy, and kinematics are all relevant in some way. We'll bring up things like energy. We'll talk about forces that are acting. In fact, forces are going to be pretty key to this, as is at least one kinematics value or some kinematics concepts. But momentum is a little more separated in that units one, two, and three had sort of levels. If we remember, like kinematics, we just look at how things move, and then things change motion and accelerate because of forces. The level below that is forces, and then forces are able to be exerted because of energy. So, unit one provides the behind the scenes for unit two, and then unit three looks further deeper than that into why forces can act. Now, momentum doesn't really do that. It doesn't tie in that way, in the way that one, two, and three are all connected for the units. But momentum is still important. It's a way to think about objects and the motion of objects that physicists very often use. All right, so when coming up with an essential question, we want to be thinking about a few different things, but one of them is motion, because momentum is going to have some moving aspect to it. Um, and the other is like the ability to change that motion, which we have already looked at, right? Forces can change the motion of an object and cause it to accelerate. Um, we haven't really gotten into for different objects that are moving, how do those different objects experience some different changes in motion themselves, like a moving bowling ball versus a moving car. And we haven't gotten into, through the lens of momentum, how that affects things. So we're going to look at some different objects. We'll have collisions between two different objects. We'll consider objects of different mass as they're moving. So we're going to phrase our central question like this: how do different objects experience different changes in motion? And in a little bit here, we're going to not only dig into different changes in motion in terms of like how much they accelerate, for example, or something like that. We're going to look at how is it different, the difficulty that we have in changing the motion of an object. Because if we accelerate it or we change its motion, how hard is that? Is it easy to change the motion of an object? Is it difficult? And along with that, we may have, depending on time and what we ended up doing in class, I sometimes do an activity to lead into momentum that asks about like what makes it easy or difficult to change the motion of an object. And um, to get at that, we're going to start with the definition of momentum itself. Now, momentum, we've maybe have heard this before, or in everyday life, the word gets thrown around sometimes, like maybe sports. I think of like that team has a lot of momentum in a sports match. And in that context, it kind of means, well, it's hard to stop them, right? They've got a lot of momentum. They're scoring a lot of points. They're doing what they want to do, and it's very difficult for the other team to stop what they're doing. So having a lot of momentum means it's difficult for someone or something to stop you from doing what you're doing. And that actually carries over pretty well. That actually connects well to the physics definition. Because back to if we did do the in-class activity before this video, I may have talked about like both mass and velocity for objects. And if something's moving really fast, it could be hard to stop that, right? Um, Picture like a rocket or something moving really fast, or a bullet train, right? Some really, really speedy, a car going 120 miles an hour. If there's something going very fast, it's hard to stop it. But mass also plays into that, right? We may have talked about like, well, if there was like a ping pong ball or a feather that was moving very fast, something very light with not a lot of mass to it, could be easy to stop it. But if there's something really big, like a train moving very fast, it's going to be very difficult to stop that object. So momentum allows us really a way to quantify way to quantify. Quantify means just put a number to it, right? So in physics, we say, well, we're going to push or pull on something. Well, how hard you push or pull is force, 20 newtons or 50 newtons or 100 newtons. We want to be able to describe, well, how big is the force? What direction are we pushing or pulling, etc. So quantifying, putting a value or number to things, it's a way to quantify motion. And we've already done that to some degree. In fact, velocity allowed us, even something like kinetic energy was a way to think about motion and say, how do we put a number to the fact that this object is moving, right? It has some velocity or it has some kinetic energy. So momentum is a way to quantify motion, and it's a way to quantify also, or how difficult it is to stop an object, or rather, we should say how difficult it is to change an object's motion. And again, velocity and kinetic energy both kind of already get at this in a way. Kinetic energy, not as much because it's a scalar, but velocity is a vector. And if you know that an object has a velocity of 20 meters per second to the right, that gives you some sense of how difficult it would be to change that motion, right? In general, we'd say if it's going really fast, harder to affect it, harder to change its motion, or if it's going really slow, probably easier. But the other thing that we mentioned a little bit ago is mass plays into this. If something's going 2 meters per second, it might be easy to stop it or change its motion, but it might be difficult if that object at 2 meters per second has a mass of 10,000 kilograms. So it's a way to quantify motion or how difficult it is to change an object's motion using both mass and velocity. And again, kinetic energy kind of gets at this because it uses mass and velocity to describe or even quantify motion of an object, like 20 joules of kinetic energy, 50 joules of kinetic energy. But the problem with kinetic energy is it doesn't tell you what direction an object is going. It's not a vector. So to quantify something in terms of how difficult it is to change the motion, it is good to know, is it going left or right, up or down? The direction becomes important for that. Because if you want to change the motion of something, um, like speed it up or slow it down, it matters whether you're pushing or pulling left, right, up, or down. The direction is important because of whatever direction the object is moving. All right, so that's momentum as a way to quantify motion or how difficult it is to change an object's motion using both mass and velocity. Now we have some equations and things for this. Obviously, mass and velocity are the two things that go into that. Now, unfortunately for us, the variable, we don't get to use m. Between capital M, lowercase m, mass has the monopoly on the variable m. We can't really spare m to use for momentum because mass is all over the place. We see a lot of mass in forces and energy, and now we're going to see more mass again. So we don't use an m here. We actually go to a lowercase p. And I know that's not even in the word momentum, so don't ask me why physicists picked that one for whatever reason. I guess if you think about the other letters, like none of them really make sense. Anyway, for whatever reason, lowercase p is our variable. So p is for momentum. It is a vector, as opposed to kinetic energy, because again, kinetic energy uses mass and velocity to describe or quantify what's going on with an object, but it's not a vector. So momentum is a vector, but kinetic energy is not. All right, units. Well, I guess we'll put the equation first, and then we'll talk about units. So to find momentum, it uses both mass and velocity, and it's just about the most simple equation we could think of, because if an object has a lot of mass, if it's really large or massive, we'd say that it has a lot of momentum, right? Something that's moving that has 1,000,000 kilograms of mass has a ton of momentum because it's hard to stop it. It's hard to change its motion. It's really difficult to affect that object. So mass has a direct relationship with momentum. If you increase the mass, you increase the momentum. So in the equation, mass just shows up on the other side of that equals sign. Likewise, if something's going really fast, if it has a ton of velocity, it also has a lot of momentum. So velocity also shows up in the numerator on the other side with a direct relationship. And there's no squared values to worry about, unlike, kinetic energy. There's nothing here that's squared. It is simply the momentum of an object is equal to the mass of that object times its velocity. Because what we're doing is we're taking into account if we're going to change the motion of this object, if, to put the sports example into context with like a 250-pound linebacker barreling at you, well, their mass is large because there's big football players, and their velocity is, well, they're probably going about as fast as they can. So there's a lot of momentum there, right? If you're going to try to block or tackle someone in football, um, that large amount of momentum comes from both the mass and the velocity of the person that's running. So yeah, our units are just interestingly enough, momentum doesn't have its own unit. We don't get like newtons for force or joules for energy or anything like that here. We actually just take the units of mass, kilograms, times the units of velocity, meters per second, and that's it. We don't change that into something else. It doesn't get turned into another unit. So maybe someday, maybe one of you will come up with a name for what this is and introduce it to the physics community, because physicists have just kind of used kilograms times meters per second for momentum, and we don't turn it into anything else. It's not like newtons or joules or what have you. Yeah, units are kilograms times meters per second. And that's momentum. Is at a basic level, we're just saying based on how much mass an object has, based on how much velocity it has, we can look at the momentum to determine things like how difficult is it to affect the motion. Okay, now we'll talk a little bit about changes in momentum. We're really going to get into this more in the next video, and I am trying to keep videos a bit shorter. I'm going to do more like multiple small videos to just with some tips and input that I've gotten and some good feedback. I think it might be a good try to yeah, keep them around 20 minutes, and then people can still watch them back to back if you want, but give you a little more of a break, right? Take 20 minutes, watch something, figure out what's going on with the basics of momentum, and then take some time to kind of digest it or think about it. So that way you're not sitting down for an entire hour or something like that for the video. So we'll see how that goes. All right. Let's see. We've got some changes in momentum to look at, and our next short video will further address this. All right, so something's moving. If you've got a moving object, um, an example could be a a grocery cart in the parking lot is rolling, and you want to stop it. So, in order to do that, right? If you see that, okay, this grocery cart has a mass of, it's not super big, right? Maybe 10, 20 kilograms at the most, so not a huge mass. Maybe 30, but probably not even that much. So 10 to 20 kilograms of mass, and this grocery cart is rolling, shopping cart is rolling at, 1 or 2 meters per second, not very fast. So you want to stop it so it doesn't hit your car or somebody's car. And you could do that by exerting a force, right? You would go and push on it or pull on it, you'd grab it. So changes in momentum, we'd say that net forces can change the momentum of objects by changing their velocity, right? Because when you grab that cart in the parking lot and you stop it, because you're helping out and you're being a good citizen and all that, um, you're changing the velocity, but you're not changing the mass, right? From this equation up here, the two ways to change momentum would be you could affect the velocity to speed it up or slow it down. That would give it a different amount of momentum. Or you could change the mass. If you suddenly remove mass from an object and there's less mass moving at the same speed that it was before, you'd have less momentum. Or you could add mass and you could have more momentum. But the reality is, and we'll look at this later, not only do we not really change the mass of objects most of the time, but also if you just drop more mass on top of something, we'll end up with like conservation of momentum equations that would show us even when you just randomly throw like a bag of groceries or like throw something heavy into that shopping cart while it's moving, it actually would still affect the velocity because of, well, conservation of momentum, which we'll get to later. But really, we don't change the mass a whole lot. Mass is not the major thing that we affect to change the momentum of objects. But by pushing or pulling with a net force, you can change the momentum by changing velocity. And there's an equation that kind of goes along with that, just to look at, well, what happens when we change the velocity of an object. So a change in momentum, which we'll spend some more dedicated time on in the next video, um, is equal to mass times change in velocity. And once again, you could, in some situations, there might be a way you could affect mass, but we're not really going to do that. And even when we do, it usually doesn't. There's a lot of cases in which like we're just going to not see a change in momentum when you affect or change the amount of mass if you add or remove mass. Changing velocity really is the way that we change momentum for objects using forces. Okay, so that equation just tells us that when you change the velocity of an object, which just as a brief reminder, we could also write this as mass times, just so we don't forget, v final minus v initial. Final minus initial will always equal the change in something, so we can use that. And this equation just allows us to say that if we multiply the change in velocity times change in mass, it'll tell us how much the momentum changed for an object. So that can be useful because AP will sometimes get at like uh, duration of time during which a force is acting or the velocity of an object is changing, and you want to look at, well, how much does that momentum change as a result? You can use the basic momentum equation, just putting a change in velocity instead of v and a change in momentum instead of just p. Okay. And what this is going to lead into in our next video is we are going to look more specifically at the forces themselves. But we'll add one more thing here. We could have one of two results, and we'll draw the example of like, I guess the shopping cart we talked about could either increase momentum, and that would look like this. So I'm just going to draw like a box, but this box could be like shopping cart that has some velocity this way. And if we put a force on it by pushing or pulling in the same direction it's already moving, that would increase the momentum. Or we could decrease that momentum. Because in the first situation, right, we've applied a force, presumably an unbalanced force. Now, really, there would be some friction probably, but we'll say there's still a net force. There's more force to the right than the left, and that causes an acceleration. That causes the object to speed up. It gets more and more momentum. Now, this would be the opposite of helping with the shopping cart. I guess if it was already rolling towards the cart storage area, and then you just pushed it to give it the last little bit to get in there, that'd probably be fine. But you don't generally want to increase the momentum of a runaway shopping cart. So if you were trying to slow it down and grab it, make it stop or to go slower, and you had that velocity going to the right, you would then put a force the other way, right? So your force would be acting this way, and by doing that, you would slow down, decrease the momentum, and cause the cart to slow or stop. So those are your two options, right? You could have a net force that either increases the momentum or decreases it, kind of similar to work. When we looked at work with forces, we said, well, positive work in the same direction the object is moving or the displacement um, increases kinetic energy, and negative work decreases it in a similar way, right? Forces acting with the velocity or against the velocity will then increase or decrease the momentum because that velocity either gets bigger or it speeds up or it slows down. Okay, sweet. So we will do more with specifically forces, and our next video is going to tie in a lot with how does force connect to changes in momentum. We're going to have something called momentum impulse theorem. We'll talk about what impulse is, but that will wait for the next one. All right, so there's some basics of momentum, what it is, the equations, how we find momentum using both mass and velocity, as well as a little bit of most AP problems aren't going to have, like, you're not just going to use P equals MV. Most AP problems are going to have changes in momentum involved in them. So, all right, don't forget to leave any questions on the Padlet in Schoology or bring them to class. And thanks for watching. We'll see you for the next one.